Okay, today I'm going to talk about the normal distribution, and the word normal here is very specific. It means a distribution which is shaped like a bell, like that, with on this axis we have frequency, and on the horizontal axis we consider it x for some variable. I'm going to do loads of different examples, but we're going to start off an example. Imagine a manufacturing company produces boxes of cornflakes. So let's just write this example. So a company produces, let's call it cornflakes boxes with mean. We're going to call the mean here mu. I'll just do in brackets mu. It's a Greek letter. And let's say that they're set to be 500 grams. So it's a manufacturing environment and they're trying to make these 500 grams. They should be symmetrical, by the way. And the mean is in the middle. So I could just write mu here in the middle, or I could write 500. I'll write mu, so it's general. Now, because this is the frequency here, there's a few features here of this curve. It's symmetrical about the mean. So what that means is the company tries to make all the cornflakes boxes around the mean, but some of them will be a little bit too light and some of them will be a little bit too heavy. Come on, visualizer, there you go. So, but the frequency gets much less when you get too low and too high. Now this doesn't just happen in a manufacturing environment, it happens in the natural world. If you took the heights of people or the weights of people or the length of fish or something, most of them would be around the mean, and then a few of them, smaller numbers, would be too big and too small, that kind of thing. Okay, so we also have at the bang in the middle, you have the mean, so that's mu. Yeah, but because this is at the highest point, it's also the mode is here, and the median. So the mode, the median, and the mean are all this value here in the middle. They're all the same. That's one of the features. The mode, the median, and the mean are all the same in a normal distribution. And it's on this axis here. So remember, this is the frequency here. I shouldn't really have an arrow there. I'm going to get rid of this arrow because it's a bit confusing to be pointing at the top of the curve. This is where the mean is. So on this axis, this x-axis, we would have grams. So I'm going to draw another... Actually, the really crucial piece of information for normal distribution is, well, there's actually two pieces of information, the mean and the standard deviation. So we need to know what that is. So I'm going to write standard deviation. I'm going to call it sigma, another Greek letter. And I'm going to say in this example, it's 10 grams. Now this brings some variation into the manufacturing process. Their machines don't get every box exactly 500 grams. There's some variation. Now, how much variation, if it's normally distributed, will be, we will know exactly. So we have the mean in the middle, and you always have 1, 2, 3 standard deviations to the right, and 1, 2, 3 standard deviations to the left. And if the standard deviation is 10, then we can put on these x values here the weights which correspond to 1 standard deviation above, 2 standard deviations above, 3 standard deviations above. So these are our x values. Now what's interesting about a normal distribution is the following. Approximately 60, is it 68%? I think it's 68% of all data. Let's try and right, fairly clearly, is within one standard deviation of the mean. Okay, so that's interesting. We know this for sure if the data is normally distributed. So between here and here, between 490 and 510, you can see that the curve is much bigger between there. And you can think of all of the data as the area under this curve. So most of it, in fact 68%, is within one standard deviation. Okay,
is that for all the time or just for
yeah, all the time. Yeah. Yeah. And then 95% is within two standard deviations of the mean. So that's between here and here. Oops. And approximately 99.7% is within three standard deviations of the mean. So that's why I only wrote 3 standard deviations to the left and 3 standard deviations to the right, because you can have some extreme values, but it's 0.3%, so that's 3 out of 1,000. Out of every 1,000 cornflakes boxes that are manufactured, roughly, typically 3 of them would be lighter than 470 and heavier than 530. Okay, right. Now we can think of another distribution, standard one. So I'm just going to draw underneath here. We use a thing called a standardizing formula to draw a similar distribution, but just with numbers of standard deviations to the right and to the left. Because not every question, that's interesting that you mentioned that there, was this always going to be like that? It actually is always going to be like that, but not every question is going to be cornflakes boxes. So this is grams. But it doesn't matter if it's about cornflakes boxes or the length of fish or the amount of time taken to do something or whatever it might be. Every normal distribution we can standardize. So they'll all look like this, and we can measure as instead of an x-axis, we have a z-axis. Again, you have frequency on the vertical, but this now is the key thing here is that the z stands for number of standard deviations from the mean. Okay, so if you're up here, if you have a z-score of 2.4, for example, then you're 2.4 standard deviations above the mean. And if, let's say, the cornflakes box was, I don't know, 524, that would correspond, in this case, to a z-score of 2.4. So every x value has a corresponding z value, and you can see it actually from the graphs, but you can work it out as well with a formula. So I'll show you what the formula is. Formula is on page 34 of your tables. It's called a standardizing formula. It allows us to convert from x to z. So it's x minus, once you know mu and you know sigma, you can convert from x to z. So it's x minus mu over sigma gives you your z value. So we have that z is equal to x minus mu over sigma. Okay, so that's your standardizing formula. Okay, I think I will just pause the video now. Okay, so we have a standardizing formula which allows us to find a z-score, a z value for any x value. And the next thing then is to show you this page 36 and 7 of the formula book, because it shows us our normal distribution, and it shows us the z-scores from -3 to +3. Now remember, z measures how many standard deviations you are away from the mean. There's no point in going more than 3 in either direction, because 99.7% of the data is within 3. But whatever z-score your particular x value has, and let's go back here and we think about, let's say 524 grams has an x value of 2.4, then you can find 2.4 on here. In fact, it goes to 2 decimal places. If it was 2.45, you go down to 2.4 and across to this. So this only goes 0 to 1. We need to go to the second page and down to 2.4. And then you have these values here, 0.9918. This is the proportion to the left of the z-score. So let's look at my graph again. If the z-score was 2.4, you're way over here, and 0.99, where's the number here? 0.9918 is the proportion in the shaded part up to your z-score of 2.4. So we can think of it in two ways. We can think of it as a proportion, but we could also think of it as a probability. It's the probability that a randomly selected cornflakes box will have weight less than 524. Or in other words, a randomly selected cornflakes box will have weight less than 2.4 standard deviations above the mean. Now, if you were asked for the probability that it has weight more than that, then you're in this white portion, and that would be the whole area underneath is 1, so the area beyond would be 1 minus this. Okay, so this table of data, all these numbers in here, 4-digit numbers, they're all probabilities or proportions, and they all give you the big proportion under the curve. So let's take a new page and we'll just do another couple of examples. So let's take an example. What is the probability that a random box has weight less than, we'll just pick a number here, 493 grams. Okay, so that's an x value. In order to do any question like that, we need to convert to a z value, because the tables, they don't know anything about cornflakes boxes, but they know about the standardized normal distribution. So we need to standardize this value. So we go 493. What is the formula, by the way? Let's go back to page 34. Z equal to x minus mu over sigma. So remember, mu in this case was 500 and sigma was 10. So z equal to x minus mu over sigma tells us that we get 493 minus 500 over 10. So that's minus 7 over 10, which is minus 0.7. And I'll just do it to 2 decimal places. I like to do my z-scores to 2 decimal places because the formula book does that. Okay, that's great. Once you know your z-score, we can know the proportion to the left or to the right. So I'll just write that in, I think. So once we know our z-score, we can find the proportion to the left or the right. So we have a standardized normal distribution. Looks like something like this. 0 in the middle, minus 1, minus 2, minus 3. We're here, minus 0.7. So we can find the proportion to the left or to the right. Now, the formula book always gives you the big proportion. Okay, so I'll write that down as well. Okay, so the formula book always gives us the big proportion. If you look here, the z-score start at 0 and go up to, let's just open up the book like this, and go up to 3. So what's happening here? Yeah, so the book of formulas only gives us the z-scores from 0 to 3. But because the distribution is symmetrical, then the distribution from 0 to minus 3 is the exact same, but the other way around. So if you have a minus z-score, then it's just the other way around. I'll show you what I mean. So the key thing here is that the formula book always gives us the big proportion. So we have a z-score of minus 0.7. We can't look at a minus z-score, so we just look at a plus z-score, and we get 0.7580. Now that's the proportion to the left or right, but it's going to be the proportion in the big part. So from our graph, here's 0.7. So the formula book is going to tell us this proportion, which is 0.7580. That's the proportion. So these four digit numbers that you see in the table are always your proportions, and they're always the proportion in the big part. That's why they go from 0.5 up to 0.999, because those are the big proportions. So I'll just mention that this is from the table. Now, if we actually wanted the proportion in here, didn't we? So this one here is going to be 1 minus 0.7580. So I'll just write that down here. If we want the small proportion, we subtract the big proportion from 1. So that's what we got, 0.7580. So what we could say, 1 minus 0.7580, which I'm going to try and do this in my head, so that's 0.2420 that's our answer. What does the answer represent? Let's write it in two ways. The probability that x is less than 493 is equal to 0.2420. That's a nice way to write it. We can also write the following. The probability that z is less than, because this is also true, minus 0.7 is also 0.2420. Okay, so these two statements mean the same thing, because your x score and your z score, they correspond to each other. This is a proportion. So what this means here is the probability that x is less than 493 is 0.2420. So in other words, if you were asked for the percentage of cornflakes boxes which were lighter than 493 grams, we would say that it's 24.20 grams. So I wish I had space for that, but I don't. Maybe I'll write it over here in a little circle, i.e. 24.20% of boxes are less than 493 grams. So that's a nice way to interpret the answer. It's a good idea to do that when you get your results. Maybe not always convert to a percentage, but just put it in the context of the question. Okay, so that's all for this video. Really, that is all the theory that you need, but you'll have to kind of play around with a few ideas to answer specific questions. But that's pretty much it. So that's all for this video.